Hey, so a lot of people are having trouble on this chapter 15, 16 test, and it is a tough chunk of material. So the yo-yo problem, and I'll show you the one that's out of the book on here, but it is very similar to a tire rolling on the ground. So when it states that it is not slipping, that means at the point of contact with the ground, this guy actually has zero velocity. So unless it's sliding around like on ice or leaving tread mark, like it's not slipping. So that means the piece of tire has the same velocity as the ground. So if the ground has zero velocity, the tire has zero velocity, and it comes from the entire thing going forward and it's rotating. So when you add together the forward motion of the entire wheel. So the entire thing is going forward, but then it's also rotating backwards around. So that rotational motion plus the forward motion, those two cancel out at the base. And so the velocity of this little point right here is zero. And when you find that, it's called the instantaneous center of rotation. That little piece of it that is not moving at all, then the velocities of every other point can be measured off of that point where the velocity is zero. So if you look at the velocity profile across the tire, the very top of it, like the whole car is going forward, and because it's also rotating, you have that rotational velocity added together to the forward motion of the car. And so you get an overall the highest velocity is happening at the top of the tire down to zero at the bottom. Okay, so if you take that tire and kind of overlay it with the yo-yo problem, so you have where it's rotating around is this point right here on the ground. And if the string has a velocity, we'll say the velocity of the string at one end of it is going to be the same as the velocity at B. So we know what the velocity of B is, and that means we know how fast our omega is, so how fast it's kind of rotating around this instantaneous center of rotation. And if you follow that velocity profile up, you can see that the center of the thing is actually moving faster than the string. And if you try this out, if you happen to have a yo-yo at home and you pull it across, so the motion of this thing, it's rolling to the left across the floor. The center is moving faster than the string, so it's actually rolling up as it's getting pulled. So if you try this out, you're pulling on the string, and it's going to be rolling up the string around that cylinder. And the difference between these two velocities, that's going to be how fast the string gets rolled together. But if we just want to look at the velocity profile across it. Okay, so it's rotating around this point here. And if we know the velocity of the string, we know the velocity of the whole thing. And you can get the velocity of every point along the center line of it. Okay, so that hopefully makes sense of which way the yo-yo is moving and what direction G is moving in. So on that quiz, G is just a velocity that's straight to the left. Okay, for these other points, so that rotational motion, I can go from the center of rotation to any point on this yo-yo, and it's going to be 90 degrees to that point. So the velocity is always tangent to that rotational motion. Okay, so going to these other points, if I go from the center of rotation to the point, and then know that the whole thing is rotating forward, F is going to be perpendicular, and H is also going to be perpendicular. So that would be the quiz solution for these ones, of which direction those velocities are. But of course, the test is going to have a different scenario, and the makeup test has a different scenario. And the important part of this whole thing is to find what it's rotating around, and then measure everything else with respect to that. That's going to be the fastest way to find that the direction of the velocities. Okay, so this actually comes from, this is the equation that you keep seeing over and over and over again through this. And let me just magnify this. So you have the velocity of some point. That point could be point F or G or H. So whatever point you want. And if we take that velocity with respect to D, velocity of D is 0. And so then the velocity of that point ends up being purely just the rotational piece of it. Okay, so this describes from D to H. This is the radius. And then we're going to have a cross product with omega, and that will give us the velocity of that point. So here's an example of that cross product. Let's figure out the velocity of point F. So F with respect to D, and that's what it comes down to in this case, because remember the velocity of D is 0. So the total velocity of F in this case ends up being just the rotation around D. So this rotation around point D, velocity is omega cross r. So here's our omega. So we are rotating around point D, and that means that our omega is going to be in the positive k direction. So if you use the right-hand rule, you're wrapping your hands around kind of that axis that's coming out of the board. So the vector for omega represents this vector right here coming out of the board. So here's your omega in that cross product. And then the position vector is going to go from the axis of rotation to the point you're interested in. So split that into x and y components. So like you might know maybe the angle here. So our x would be our cosine theta and our y would be our sine theta. You can break that vector into x and y components. And then to get this relative rotational velocity, you would then crank through this cross product. So you can kind of think of the signs of this thing. So if we're going at negative in the x direction and positive in the y direction, so let me put in some of those signs. So this is going to the left and up on here. And then omega is counterclockwise, so omega is going to be positive. And what direction of motion that is going to end up giving us. So for the I direction, remember how to do cross products. For I, we're going to go 0 minus omega cross W. So in the I direction, we're going to end up being negative. See that negative velocity in the I direction? And that's true. If you look at this brown arrow, it's going negative in the I direction. So then if we look at what's happening in the J direction, and remember when you take cross products for the J direction, you go the opposite way. So if I'm going to do J, it's K times X minus I times J. So you have plus times a negative. So you end up with a negative velocity in the J direction as well. So that would be the negative I, negative J, and those two would add together to the overall velocity of what F is doing here. So that's the velocity of F is the rotation around D, and it's omega cross R. So the R goes from the point of rotation to the point you're interested in. So split things into X, Y, Z components and walk through that cross product. Okay, let's say that we're going to, instead of taking the velocity with respect to point D, let's say we take the velocity with respect to point A instead. So A is the center of the tire, and that's which way the car is moving. So let's say we know that the car is going 60 miles an hour or something, and we're just going to take the velocity relative to this point instead. So with respect to A, so that means we're going to be adding together the velocity of A. Let's leave that as our red vector. So for each of these points, we're going to be adding what A is doing, and then this blue piece is the rotation of the point with respect to A. So if this tire was just spinning in place, this blue piece, that is the relative velocity of each point with respect to A. And if we add those two velocity vectors together, head to tail, that will give us the overall velocity of this thing. And you can see that no matter which way you do this, so if I take the velocities relative to D, I get the same result as if I get the velocity by taking and adding what A is doing to that rotational piece. So I can add these two, blue plus red is equal to orange, or I can just take the motion with respect to B, and it adds together to the same magnitude. So either way you do it, you can get the velocity of any point from the velocity of any other point if you just add on that rotational motion. So this is these equations, this is the big deal for that chapter.